Hello, dear traveler. Welcome back to the sleepy circle. If you step outside tonight, the air is crisp and cold. High overhead, the winter stars are blazing. You might see Orion the hunter standing tall and proud in the darkness, guarding the night. But this story isn't about what we can see right now. It's about what is missing. You see, Orion is safe in our sky tonight because his greatest enemy is gone, buried deep beneath the horizon, waiting. Tonight, we're going to look beyond the winter chill. We're going to travel forward in time to the warm nights of summer to meet the ancient rival who chases the hunter from the heavens. Tonight, we meet the Scorpion, Scorpius. Why talk about a summer constellation in the dead of winter? Because to understand the sky, we have to understand its cycles. We have to understand why Orion flees as spring approaches. We have to understand the invisible geometry that keeps these two titans, the hunter and the scorpion, locked in an eternal dance where they can never, ever meet. We'll dive into the myth of their ancient battle. We'll explore the red supergiant heart of the scorpion, Antares, a star so massive it dwarfs our own sun. And we'll discover how the Earth's own motion creates this cosmic game of hide and seek. If you like to make this journey even more memorable, check out the description for the free One Thing sheet, digital or print-friendly versions, where you can jot down just one key idea from tonight's story, like why Scorpius and Orion never meet. It is for those who enjoy slow, lasting learning. Or just simply drop a comment below. We'd love to hear what you take from tonight's story. And subscribe for more cosmic bedtime stories. So, wrap yourself up warm. Settle in. Even though the winter wind is blowing outside, in our circle, we can travel anywhere and any when. Are you ready to meet the shadow that waits for summer? Let's look up and follow the chase. What if I told you that two enemies have been chasing each other across the sky for 3,000 years? Not in legend, not in stories, but right now, tonight, above your head. When Scorpius rises in the east, Orion flees below the western horizon. When Orion returns in winter, Scorpius vanishes. They never share the same sky, ever. The ancient Greeks called this the eternal chase. But here's what they didn't know. This cosmic pursuit isn't magic, it's geometry. It's physics. It's the Earth itself spinning through space, turning myths into mechanics. So what really causes this celestial separation? Why do certain stars belong to certain seasons? And what can a scorpion and a hunter teach us about time, motion, and our place in the universe? Tonight, we follow the chase. The legend of Scorpius. Who was the scorpion that defeated the mightiest hunter in mythology? Picture ancient Greece. No electricity, no screens, just firelight and stars, thousands of them burning overhead like scattered embers. In those days, the sky was not decoration, it was calendar, compass, and cathedral. And among all the constellations, none was more feared than Scorpius. Let me tell you why. There once lived a giant named Orion, son of Poseidon, god of the sea, and Euryale, a Gorgon. He was born with the ocean in his blood. He could walk across water without sinking, stride through storms, hunt beasts no mortal could touch. Orion was magnificent, and he knew it. He traveled the world slaying lions, serpents, wild bulls. His fame spread across every kingdom. When he arrived on the island of Crete, even the goddess Artemis, huntress of the moon, fell in love with him. Together they roamed the forests, arrow and bow, tracking prey beneath silver moonlight. But Orion's pride grew monstrous. He began to boast. "There is no creature I cannot kill," he declared, "no beast born of earth that can defeat me." The earth heard him. Mother Gaia, ancient goddess of all living things, took offense. How dare a half-mortal claim dominion over her children? So she reached into the darkest caves, the deepest crevices, and summoned something terrible. A scorpion. Not an ordinary scorpion. This was a creature of divine vengeance, armored in black shell, its tail dripping with poison that could kill gods. The scorpion found Orion. The battle was fierce. Orion swung his sword. The scorpion circled, striking with its tail. Hours passed, then days. Orion, for the first time in his life, felt fear. He ran. He fled to the shore, waded into the sea, swam until he was just a speck on the horizon. Apollo, the sun god and brother of Artemis, watched this unfold. He despised Orion, jealous perhaps of his sister's love. He saw his chance. He found Artemis on a cliff overlooking the water. "Sister," he said, "you claim to be the greatest archer, but can you hit that distant speck upon the waves?" Artemis, proud and unaware, fitted her silver arrow. She drew, she released. The arrow flew true. Orion died with his lover's arrow through his skull. When the tide brought his body to shore, Artemis wept. She begged Zeus, king of the gods, to honor Orion among the stars. Zeus agreed. He placed Orion in the winter sky, bright belt, raised sword, faithful hunting dogs at his feet. But here is the twist. Zeus also honored the scorpion, for it had humbled the proudest hunter. Scorpius was placed among the summer stars, its red heart, Antares, blazing, its curved tail poised to strike. And to prevent further conflict, Zeus separated them forever. When Scorpius rises, Orion sets. When Orion rises, Scorpius sets. They chase each other across the heavens, never meeting, never resting. Now, before we continue, a brief note on names. The Greeks told these stories first: Zeus, Poseidon, Artemis, Gaia. But when the Romans adopted Greek mythology, they renamed the gods. Zeus became Jupiter, Poseidon became Neptune, Artemis became Diana, Gaia became Terra. Since we use the Latin names for our constellations and planets today, you'll often hear these stories told with Roman names, but make no mistake, these are Greek myths at their heart, passed down through Roman culture to reach our modern sky. But wait, if this is just a story, why does it actually happen? Why can't we see Orion and Scorpius together? The scorpion was created to humble the proudest hunter, but its real lesson isn't about monsters, it's about cosmic geometry, which we'll uncover next. Understanding the celestial arrangement. What is the actual celestial relationship between Scorpius and Orion? Let's step back from myth and look at the sky as the Greeks actually saw it. The night sky has changed very little since ancient times. The stars moved through the night from east to west, just as the sun did. If you went out at the same time every night, you would notice a larger movement, progressing slowly from east to west over days, weeks, and months. Yet if you went out at 9 o'clock on the evening of March 7th every year, the same pattern of stars would greet you. This regularity allowed the ancients to use stars for predicting when to plant crops, when to harvest, when to expect cold weather, and when spring was close at hand. The constellation Scorpius lies low in the summer sky, south of Ophiuchus, the serpent bearer, east of Libra, the scales. Its bright red star Antares, whose name means rival of Aries because of its ruddy color, marks the heart of the scorpion. From Antares, a line of stars curves toward the horizon before hooking back to form the distinctive stinger. Orion, by contrast, dominates the winter sky. His 4 bright stars form a body. His 3-star belt is unmistakable. Red Betelgeuse marks his shoulder. Blue Rigel blazes at his foot. The fuzzy patch in his sword, that's the Orion Nebula, a stellar nursery where new suns are being born. Now here's the key insight. Orion and Scorpius sit on nearly opposite sides of the celestial sphere, roughly 180 degrees apart. Think of it like 2 cities on opposite sides of Earth. When one faces the sun, the other faces darkness. As Earth rotates, we can only see half the celestial sphere at any moment. The half facing away from the sun is visible as our night sky. Since Orion and Scorpius are antipodal, opposite each other, when one is in our night sky, the other is in our day sky, hidden by sunlight. But there's more. The Earth doesn't just rotate daily, it also revolves around the sun yearly. This revolution changes which half of the celestial sphere faces us at night. In December, Earth's night side faces toward Orion's region of space. We see him rise majestically in the east, march across the southern sky, and set in the west. Scorpius, meanwhile, is behind the sun, invisible, drowned in daylight. In June, everything reverses. Now Earth's night side faces Scorpius. The scorpion rises in twilight, dominates the summer sky, while Orion hides behind the sun. The eternal chase isn't supernatural. It's inevitable geometry, a consequence of their placement on opposite hemispheres of the celestial sphere. combined with Earth's double motion of daily rotation and yearly revolution. So the gods didn't separate them, geometry did. But why are certain stars associated with certain seasons at all? What determines a summer or winter constellation? Orion and Scorpius appear opposite because they are opposite, positioned 180 degrees apart on the celestial sphere. Earth's rotation and revolution ensure they can never share our night sky. The celestial sphere concept. What is the celestial sphere, and why did ancient astronomers invent it? To a naive observer, it's not obvious that the sky has any particular shape. The Egyptians often represented the sky as the goddess Nut, arched over the land, sometimes with a flattened back. But the Greeks saw something different. They noticed that stars move on parallel circles, climbing together from the eastern horizon, crossing the sky, going down together in the west. Even more suggestive were the circumpolar stars, those near the North Star, which could be seen all night long, moving in circles around the celestial pole. From these observations, Greek astronomers developed one of humanity's most powerful mental models, the celestial sphere. Imagine standing at the center of a vast, hollow globe. The stars are painted on the inside surface of this globe, all at the same immense distance. The Earth sits at the center, tiny, stationary. The entire sphere rotates around us once per day, carrying all the stars with it from east to west. This model is, of course, wrong in its physics. The Earth moves, not the stars, but it's brilliantly useful for observation. Every prediction you can make with the true model, rotating Earth, you can also make with a celestial sphere model. For practical astronomy, it makes no difference. The celestial sphere has several crucial features. The celestial poles. Directly above Earth's North Pole lies the North Celestial Pole, the point around which all stars appear to rotate. Today, Polaris sits nearly at this point, making it the North Star, but this wasn't always so. Earth's axis wobbles slowly over 26,000 years, a motion called precession, so different stars have served as pole stars throughout history. The celestial equator, an imaginary circle running around the celestial sphere directly above Earth's equator. It divides the sphere into northern and southern hemispheres. The ecliptic, the path the sun appears to trace across the celestial sphere over a year. It's tilted 23.5 degrees from the equator because Earth's axis is tilted. This tilt is why we have seasons and why different constellations dominate at different times of year. The zodiac, a band of 12 constellations straddling the ecliptic. As Earth orbits the sun appears to move through these constellations, spending about a month in each. Scorpius is one of these zodiacal constellations. The celestial sphere was first described systematically by Eutyches of Cnidus around 370 BC. His work inspired the poet Aratus to write The Phenomena, a verse description of the constellations that remained popular for centuries. Aratus described how the four principal circles, equator, ecliptic, and the two tropic circles organized the heavens. So we have a mental model, but how does this model explain what we actually see? Stars rising, crossing, setting. Why don't all stars behave the same way? The celestial sphere is an imaginary construct that maps the positions of all celestial objects. Though the stars aren't really on a sphere, this model perfectly predicts their apparent motions. Diurnal motion. How stars move each night. Why do stars rise in the east and set in the west? And why do some stars never set at all? In a day and a night, the stars describe circles about the celestial pole. If you watched the sky from sunset to sunrise, every star would trace an arc across the heavens. But not all arcs are equal. Stars near the pole trace small circles, so small they never dip below the horizon. These are called circumpolar stars, and from northern latitudes they include Polaris, the stars of Ursa Major, the Big Dipper, and Cassiopeia. They wheel around the pole continuously, visible every clear night of the year. Stars farther from the pole trace larger circles, circles that pass below the horizon. These stars rise and set. The farther south a star lies on the celestial sphere, the less time it spends above the horizon for northern observers. At the equator, something remarkable happens. If you stood on Earth's equator, the celestial poles would lie on your horizon, one due north, one due south. The celestial equator would pass directly overhead. Every star would rise exactly in the east, climb straight up, pass overhead, and set exactly in the west. Every star would spend exactly 12 hours above the horizon and 12 hours below. Medieval astronomers called this the right sphere because stars move perpendicular, upright to the horizon. At the poles, the situation is reversed. At Earth's North Pole, the North Celestial Pole is directly overhead. Stars don't rise or set at all. They circle parallel to the horizon. Half the celestial sphere is permanently visible, half is permanently hidden. This is called the parallel sphere. At intermediate latitudes, where most of us live, the sphere is oblique. The pole is neither overhead nor on the horizon, but somewhere in between. Its altitude above the horizon equals your latitude. In Seattle or Paris, latitude 48 degrees north, the northern celestial pole is 48 degrees above the northern horizon. This oblique orientation creates the familiar pattern: stars rising in the northeast or southeast, arcing across the southern sky, setting in the northwest or southwest. Stars on the celestial equator, like the stars of Orion's belt, rise exactly east and set exactly west, spending 12 hours up and 12 hours down, regardless of season. Ptolemy, around 150 AD, noted that this daily motion could be demonstrated with a simple sighting tube, a hollow tube aimed at a star. After 20 minutes, the star will have moved out of view, but aim the tube at Palamas and the star remains centered all night, proof of the celestial pole's existence. This diurnal rotation explains why stars rise and set, But it doesn't explain why Orion is a winter constellation and Scorpius a summer one. For that, we need to understand the annual motion. Diurnal motion is Earth's daily spin, but there's another motion, slower, subtler, that determines which constellations rule each season. Earth's rotation causes stars to rise in the east and set in the west. Your latitude determines which stars are circumpolar and which rise and set. But this daily motion affects all stars equally. It doesn't create seasonal constellations. The Earth's orbit and seasonal sky. Why do different constellations appear in different seasons? Here's a thought experiment. Stand outside at sunset tonight and note which stars are rising in the east. Come back tomorrow at the same time. The same stars will be rising, but about 4 minutes earlier. After a week, those stars rise nearly half an hour earlier. After a month, 2 hours earlier. After 1 year, the stars are back exactly where they started. This annual cycle is caused not by Earth's rotation, but by Earth's revolution around the Sun. As we orbit, our planet's night side faces different directions in space. Each night, we peer out at a slightly different slice of the celestial sphere. The sky we see at night has changed very little since the time of the ancient Greeks. It was easy for them to see that stars moved through the night from east to west, just as the sun did. If you went out at the same time every night, you would notice a larger movement that progressed slowly from east to west over days, weeks, and months. Let me make this concrete. In December, Earth is positioned on one side of its orbit. At midnight, we face outward toward the region of space where Orion, Taurus, and Gemini reside. These constellations appear high in our winter sky. The opposite direction, toward Scorpius, Sagittarius, and the summer constellations, points toward the sun. We can't see those stars because they're up during the day, washed out by sunlight. In June, Earth has traveled halfway around its orbit. Now at midnight, we face the opposite direction, towards Scorpius and Sagittarius. These become our dominant constellations. Orion, he's now in the direction of the sun, invisible. This is why we have seasonal constellations, not because the stars themselves move, but because Earth's changing position gives us changing windows onto the cosmos. The sun appears to drift eastward against the background stars, completing one full circuit through all 12 zodiac constellations in 1 year. This apparent path is the ecliptic. When the sun is in Scorpius, roughly November-December, Scorpius is invisible, drowned in daylight. 6 months later, Scorpius is opposite the sun and dominates the midnight sky. Ancient astronomers paid close attention to when stars first became visible at dawn after being hidden behind the sun. This morning rising, or heliacal rising, was a key calendar marker. The heliacal rising of Sirius, the dog star, marked the beginning of summer's hottest days, the dog days. The Pleiades morning rising signaled harvest time in May. The regularity of these appearances allowed ancient cultures to create calendar systems based on star risings. A document called a parapegma would list day by day which stars rose or set, and what weather or seasonal events to expect. Now we understand why Scorpius and Orion swap places seasonally. But why is Antares, the heart of Scorpius, so red? What kind of star is it? Seasonal constellations result from Earth's yearly orbit around the Sun. As we revolve, our nightward view shifts, making different parts of the celestial sphere visible at different times of year. The zodiac and the ecliptic path. What is the zodiac, and why do the sun, moon, and planets travel along it? The zodiac is not mere astrology. It's one of the most ancient and practical inventions in astronomy. The word comes from the Greek zodiakos kyklos, circle of animals. It's a belt of 12 constellations straddling the ecliptic, the sun's apparent annual path. Because the moon and planets orbit roughly in the same plane as Earth, they also stay close to the ecliptic, which means they're always found wandering through the zodiacal constellations. Scorpius is one of these 12. Its placement makes it special. It's one of the few constellations the sun, moon, and planets actually pass through. The origins of the 12 constellation zodiac trace back to Babylon after 900 BC, though individual constellations are older. The Greeks adopted the zodiac virtually whole from the Babylonians in the 5th century BC. Meanwhile, ancient India developed a parallel and equally sophisticated system around the same era or earlier. The Vedas describe 27 or 28 nakshatras, lunar mansions dividing the ecliptic into equal segments of about 13.33 degrees each. These are conceptual regions along the moon's path defined by key visible stars, yoga taras, like bright Aldebaran, Rohini, Betelgeuse, Ardra, Regulus, Maga, Spica, Chitra, and especially Antares, Alpha Scorpii, as the key star for Jyesta Nakshatra, marking the Scorpion's region. Though not distinct constellations like the zodiac signs, nakshatras served as precise celestial longitude markers for calendars, predictions, and navigation, much like Babylonian star paths. About 10 to 12 nakshatras feature prominent naked-eye stars, magnitude less than 2.5, making them observable without telescopes, e.g. Rohini near Aldebaran, mag. 0.9, Jyesta near Antares, mag. 1.1. Modern tools like Stellarium overlay these boundaries, revealing their enduring utility. Indian astronomy thus contributed foundational ideas to global star tracking traditions, influencing timekeeping across cultures. Consider the ancient observations encoded in the zodiac. The Babylonians called Taurus Ga-Ana, the bull of heaven. Gemini was Mas-Tababa Galgal, the great twins. Scorpius was one of the most prominent, its distinctive hook of stars easily recognizable low in the southern summer sky. The Greeks divided each zodiacal constellation into 30 degrees, creating 12 signs of 30 degrees each, a complete 360-degree circle. The sun moves through roughly 1 degree per day, spending about a month in each sign. The ecliptic crosses the celestial equator at 2 points, the vernal or spring equinox and autumnal equinox. On these days, the sun rises exactly east and sets exactly west. Day and night are equal everywhere on Earth. The solstices mark the sun's extreme northern and southern positions. At summer solstice, around June 21 in the northern hemisphere, the sun is highest in the sky, days are longest. At winter solstice, around December 21, the sun is lowest, nights are longest. These 4 points, 2 equinoxes and 2 solstices, divide the year into 4 seasons. The lengths of these seasons are not exactly equal, a fact the Greeks knew precisely. Spring, 94.5 days in Hipparchus's time. Summer, 92.5 days. Autumn, 88 1/8 days. Winter, 90 1/8 days. This inequality reveals something profound. The sun doesn't travel at constant speed along the ecliptic. It moves faster in winter when Earth is closer to the sun, and slower in summer when Earth is farther. This is the solar anomaly, and explaining it was one of the great challenges of ancient astronomy. The zodiac connects Scorpius to time itself, to seasons, calendars, and agriculture. But what makes Antares, its heart star, burn so red? The zodiac is the sun's annual path through 12 constellations. Because the moon and planets orbit in nearly the same plane, they too traverse this belt, making the zodiac the celestial highway of our solar system. Antares, the heart of the Scorpion. What kind of star is Antares, and why does it glow red? Antares is the 16th brightest star in the sky and the 4th brightest near the ecliptic. Its name means anti-Aries, or rival of Aries, because its reddish color resembles the red planet named for the Greek god of war. When Mars wanders near Antares, as it does every couple of years, the two red lights compete for attention. But Antares isn't just red, it's enormous. Antares is a red supergiant star, one of the largest stars visible to the naked eye. If you placed Antares where our sun is, its surface would extend past the orbit of Mars, engulfing Mercury, Venus, Earth, and Mars entirely. The asteroid belt would lie just outside its atmosphere. Why so red? Stellar color indicates surface temperature. Blue stars are hottest, over 20,000 K. White stars are intermediate. Yellow stars, like our sun, are cooler, about 5,800 K, and red stars are coolest, around 3,500 K or less. But cool is relative. Antares' surface is about 3,500 Kelvin, cool for a star, but still hot enough to vaporize any known material. The reason for this relative coolness is the star's enormous size. Antares has expanded so much that its outer layers have spread thin and cooled. Antares is also a binary system. It has a blue-white companion star. This companion is itself quite bright, but is overwhelmed by Antares' ruddy glare. Resolving this binary requires large telescopes and high magnification. The red glow of Antares tells us something about stellar evolution. Giant red stars like Antares are near the end of their lives. They've exhausted the hydrogen in their cores and are now fusing heavier elements. Eventually, within the next million years, Antares will explode as a supernova, briefly outshining entire galaxies. When that happens, Scorpius will have a new heart, a collapsed neutron star, or perhaps a black hole, surrounded by an expanding shell of gas that seeded the cosmos with heavy elements. Antares, like Orion's Betelgeuse, is dying. Two ancient enemies, both nearing their cosmic end. What does star death actually look like? Antares is a red supergiant, an enormous dying star whose cool surface creates its distinctive color. Its eventual supernova will scatter elements across space. How stars are born. Where do stars come from? Every star you see, including Antares, including our sun, was born from a cloud of gas and dust. Not metaphorically, literally. The space between stars isn't empty. It's filled with diffuse hydrogen, traces of helium, and tiny grains of cosmic dust. In certain regions, this material collects into vast clouds called molecular clouds or nebulae. The Orion Nebula, visible as a fuzzy patch in Orion's sword, is one such stellar nursery, actively forming new stars right now. Here's how it happens. Step 1. Collapse. Something disturbs the cloud, perhaps a shock wave from a nearby supernova or the gravitational tug of a passing star. Parts of the cloud begin to collapse under their own gravity. Step 2. Fragmentation. As the cloud collapses, it breaks into smaller clumps. Each clump continues collapsing independently. These clumps are the seeds of future stars. Step 3. Heating. As a clump collapses, its interior heats up. Gravitational energy converts to thermal energy. The center grows hotter and denser. Step 4. Protostar. Eventually, the core becomes hot enough and dense enough to glow, but it's not yet a true star. This is a protostar, still contracting, still heating. Step 5. Ignition. When the core temperature reaches about 10 million Kelvin, hydrogen nuclei begin fusing into helium. Energy floods outward. A star is born. The time from initial collapse to hydrogen ignition takes millions of years. Our sun went through this process about 4.6 billion years ago. The Orion Nebula is producing new stars right now. We can see protostars embedded in the glowing gas. But not all stars are alike. The mass of the original clump determines everything. Low-mass clumps produce red dwarf stars, small, cool, dim, but incredibly long-lived. They burn their fuel so slowly they'll shine for trillions of years. Medium-mass clumps produce stars like our sun, yellow, moderate temperature, with lifetimes of about 10 billion years. High mass clumps produce blue giants and supergiants, intensely hot, incredibly luminous, but short-lived. They burn through their fuel in mere millions of years. Antares came from a high-mass clump. It was born a brilliant blue star, burned furiously for a few million years, then expanded into the red supergiant we see today. It's old for a massive star, nearing death. Stars are born from collapse, but what happens when they die? Do they just fade away? Stars form when gravity collapses clouds of gas and dust until nuclear fusion ignites in their cores. The mass of the cloud determines the star's size, color, temperature, and lifespan. Stellar death and rebirth. How do stars die, and what do they leave behind? Every star eventually runs out of fuel. What happens next depends on its mass. Low-mass stars, like red dwarfs, these burn so slowly they haven't had time to die yet. The universe isn't old enough. Red dwarfs formed at the beginning of time are still shining today. Medium-mass stars, like our Sun, when the core hydrogen is exhausted, these stars swell into red giants. They shed their outer layers into space, creating beautiful planetary nebulae, shells of glowing gas. The core contracts into a white dwarf, a dense stellar corpse about the size of Earth but with the mass of the Sun. White dwarfs cool slowly over billions of years, eventually fading into cold black dwarfs. High-mass stars, like Antares, these live fast and die spectacularly. After exhausting hydrogen, they fuse heavier and heavier elements, helium into carbon, carbon into oxygen, oxygen into silicon, silicon into iron. But iron is the end of the line. Fusing iron doesn't release energy, it absorbs it. With no energy supporting it, the core collapses catastrophically. In less than a second, the core compresses to nuclear density. The outer layers crash inward, rebound off the ultra-dense core, and explode outward in a supernova, one of the most violent events in the universe. For a few weeks, a supernova can outshine an entire galaxy, billions of stars. What remains? If the original star was moderately massive, the core becomes a neutron star, a city-sized ball of neutrons spinning rapidly and emitting beams of radiation. Some neutron stars appear as pulsars, flashing like cosmic lighthouses. If the original star was extremely massive, even neutron pressure can't halt the collapse. The core becomes a black hole, a region of space where gravity is so intense that not even light can escape. The cosmic cycle. Here's the beautiful part. When a supernova explodes, it scatters heavy elements, carbon, oxygen, iron, gold, across space. These elements mix into the interstellar medium, enriching the gas clouds from which future stars will form. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was forged in the cores of massive stars and scattered by supernovae. You are quite literally made of star stuff. Antares will explode someday, perhaps tomorrow, perhaps in 100,000 years. When it does, it will seed space with the elements needed for new planets, new life. The Scorpion's heart is a dying star. The hunter's shoulder, Betelgeuse, is also dying. Two ancient enemies, both nearing supernova. Their deaths will create the raw materials for new worlds. Stars die according to their mass, becoming white dwarfs, neutron stars, or black holes. Supernovae scatter heavy elements across space, seeding future generations of stars and planets. Observing Scorpius. How can you find and observe Scorpius in the sky? Scorpius is one of the most distinctive and rewarding constellations to observe if you know when and where to look. Scorpius is a summer constellation for Northern Hemisphere observers. It's best visible from May through August, reaching its highest point around midnight in mid-June. However, because it lies far south on the celestial sphere, it never climbs very high above the southern horizon for observers at northern latitudes. Face south on a summer evening, look low on the horizon for a distinctive fishhook pattern of stars. Antares, bright and noticeably red, marks the heart. From Antares, follow a curving line of stars eastward and downward toward the horizon before the line hooks back upward to form the stinger. From latitudes above 45 degrees north, like Seattle, Paris, or Minneapolis, the southern parts of Scorpius barely clear the horizon. The stinger may be invisible. Travel south to the American Southwest, Mediterranean, or Southern Hemisphere to see Scorpius in its full glory. Scorpius contains 4 Messier objects, all visible with binoculars or small telescopes. M4, a globular cluster near Antares, easy to find. M6, butterfly cluster, open cluster near the stinger. M7, Ptolemy's cluster, bright open cluster known since antiquity. M80, a more distant globular cluster. Scorpius is best photographed from dark sites with clear southern horizons. Even a simple camera on a tripod with a 15-second exposure at ISO 1600 can capture the constellation's shape and Antares' distinctive color. Scorpius is best observed in summer, low in the southern sky. Its distinctive fishhook shape, red heart Antares, and multiple star clusters make it a rewarding target. The Eternal Chase Revisited. Let's return to where we began. 2 enemies chasing each other across the sky for 3,000 years. We now understand why. Orion and Scorpius occupy opposite hemispheres of the celestial sphere, separated by roughly 180 degrees. Earth's daily rotation causes all stars to rise and set, but it's Earth's yearly revolution that determines which constellations dominate each season. In winter, Earth's night side faces Orion's region of the celestial sphere. In summer, it faces Scorpius. They swap, forever trading places because geometry demands it. But the ancient story captures something deeper. The Greeks saw Orion as the ultimate hunter, powerful, skilled, proud. Too proud. His boast that no beast could defeat him was hubris, the sin of excessive pride. Earth sent the Scorpion not as random monster, but as cosmic correction, a reminder that even the mightiest can fall. Today, both Orion and Scorpius contain dying stars. Betelgeuse, Orion's shoulder, and Antares, Scorpius's heart, are both red supergiants nearing the end of their lives. Within cosmic timescales, perhaps 1,000,000 years, both will explode as supernovae. The eternal chase has an ending. When Antares explodes, the Scorpion will have a new heart, perhaps a neutron star, perhaps a black hole. The constellation's shape will endure, but its character will change. And from the scattered debris, from the iron and calcium and oxygen, new stars will form, new planets, perhaps new life. The eternal chase is real, driven by celestial geometry. Both hunters and hunted are mortal, their stars aging, approaching death. But from their endings, new beginnings emerge. What the sky teaches us. What can the story of Scorpius and Orion teach us about our own lives? We've traveled from myth to mechanics, from ancient Greece to stellar nurseries. But the journey isn't complete without asking, what does this mean for us? Lesson 1. Pride has consequences. Orion's boast, "No beast can defeat me," brought his downfall. The universe doesn't care how powerful you think you are. There's always something bigger, something you didn't account for. Humility isn't weakness, it's wisdom. Lesson 2. Opposites are connected. Orion and Scorpius can never meet, yet they define each other. Without winter, we wouldn't appreciate summer. Without darkness, we wouldn't see stars. The things that seem most opposed are often most intimately linked. Lesson 3. Everything is in motion. Nothing in the cosmos is static. Earth rotates, Earth revolves. Stars are born, age, and die. The constellations themselves slowly change shape as stars drift through space. The eternal chase isn't eternal, it just seems that way from our brief human perspective. Lesson 4. Destruction creates. Antares will someday explode, so will Betelgeuse. These deaths sound catastrophic, and they are, but they're also generative. Supernovae seed space with heavy elements, making possible the rocky planets and living creatures that follow. Your body contains atoms forged in exploding stars. death, and birth are cosmically intertwined. Lesson 5. We are part of the story. The ancient Greeks looked up and saw patterns. They told stories. Those stories helped them understand time, predict seasons, navigate oceans. We look up with different eyes, telescopes, spectrometers, space probes. But we're doing the same thing, making sense of a universe that doesn't owe us explanations. You are standing on a small planet orbiting an ordinary star in a galaxy of 400 billion stars in a universe of trillions of galaxies, and yet, impossibly, you can look up and understand why certain constellations appear in certain seasons. You can trace the nuclear reactions that created your atoms. You can tell stories that connect you to ancestors who told stories about the same stars. Tonight, when you look up and see Scorpius hanging low in the summer sky, what will you see? A random pattern of stars? A monster that defeated a hero? Or the heart of a dying giant surrounded by clusters of younger stars participating in a cosmic drama that began before Earth existed and will continue long after we're gone? The chase continues. It always does, but now you know why. The scorpion rises. The hunter sets. Summer becomes winter. Winter becomes summer. Stars are born. Stars die. From their ashes, new stars rise. The eternal chase isn't punishment, it's pattern. The universe moves in cycles, day and night, summer and winter, birth and death and rebirth. Right now, while we freeze in January, the scorpion is hidden. But the earth is turning. The seasons are drifting. And slowly, inevitably, Orion will begin to dip lower in the west. And Scorpius will begin to rise in the east. And somewhere on a small blue planet, creatures made of stardust look up and tell stories about the lights in the sky. As the Greeks told stories, as the Babylonians told stories, as every culture in every age has told stories, because the stars don't just shine, they teach. Here at the Sleepy Circle, we love these stories. They remind us that the sky is a clock, vast and perfect. That winter always gives way to spring, and spring to summer. That what is hidden will always return. I'm curious, when you look at Orion tonight, will you see him differently? Will you see a hero at the height of his power, or a hunter running out of time, knowing his rival is on the way? Tell me in the comments which season of the sky you prefer, the brilliant diamonds of winter or the warm, hazy treasures of summer. I read every thought you share with our circle, and if you want to be ready when the sky changes, please subscribe. We have a whole universe left to explore. For now, enjoy the winter stars. Let Orion shine bright for you tonight, but keep an eye on the horizon, because the days are getting longer and the scorpion is waking up. The chase never ends. Neither does the wonder. Sleep well, stargazers, and keep looking up.